Hi everyone. So in this video I'm going to go over the final two chapters of General Chemistry 2. I assume you're familiar with these videos by now, so I'm not going to spend too much time talking about how they work and stuff like that. However, I just want to say congratulations on being almost done with General Chemistry, and I hope that we'll see some of you in Organic in the future. So with that said, I would like to go ahead and get started and go over this 20 question practice set. So it says, which of the following statements are true? The first one is a spontaneous reaction is always a fast reaction. This is absolutely not true. Delta G says nothing about rate. So delta G says nothing about rate. A very famous example of this is diamond turning into graphite. The delta G for diamonds turning into graphite is negative, so it should be spontaneous. In fact, it is spontaneous. However, the rate at which a diamond turns into graphite might be 10 million years, right, for any substantial amount to change. So therefore, even though it's spontaneous, it's really slow. But again, delta G tells us nothing about the rate, so this is definitely not the correct answer. There is a heat tax for every energy transaction. This is true. There are lots of examples of this, but the one I'm going to give is a car. A car driving down the road, as you know, the engine gets hot. Well, that engine getting hot requires energy. So gasoline is being burned to make the engine hot, but that engine is not propelling the car down the road. Essentially, in this transaction, we've paid a heat tax because we didn't get the energy to do what we wanted to do. And it turns out that this heat tax is true in all of these energy transactions. The other thing to point out about this is that this is why it's often thought of as if there are less conversions of energy from one form to another, overall we pay less heat tax. And that's true most of the time. Letter C says, the entropy of a system always decreases for a spontaneous process. And that is not true. It always increases for a spontaneous process. And this is the second law of thermodynamics. So basically it just said it backwards. So that's not true. And of course, none of the above are true. Can't be the answer because we found that choice letter B is the correct answer. Question 2 says, blank is a thermodynamic function that increases with the number of energetically equivalent ways to arrange components of a system to achieve a particular state. So this is the very technical definition of entropy. But let's go through all of these answers. So free energy is the capacity to do work. Heat of a reaction is essentially enthalpy. Entropy is the answer to this question. Entropy is more generally thought of as randomness. The idea here is that things progress towards randomness. And a common example of this is if you look at what happened in Chernobyl in Russia. And not the actual nuclear meltdown, but one day there was a city that had a lot of people in it. Then something bad happened and all those people had to leave. If you were to go back to that city today, everything would be more random, right? The roads might have grass growing or even trees growing in them. The buildings would be falling down. Unless we put in work, randomness always wins. So humans put in work to decrease randomness, right? If you think of common examples around here, the roads get potholes because randomness is where nature is headed, and then human beings come along and fix those potholes. So that's the more practical definition of entropy. And if you want to think about this one final way, you can think about it statistically. So there are an infinite number of disordered roads, for a road example, with cracks and potholes and all this kind of stuff. But there's only one perfectly smooth road. So statistically, you're a lot more likely to be not perfectly smooth than you are to be perfectly smooth. So human beings have to put in work, whether it's people or machines people make, have to put in work to fight against entropy. Enthalpy is essentially the heat energy of a chemical process, and molar equivalence has nothing to do with anything here. Number 3 says, which of the following processes shows a decrease in entropy of the system? And if you haven't already, I would suggest you watch question 2, because in question 2 I discuss kind of the practical definition of entropy. Question 2 has the, physics, if you will, definition, or the very technical definition of entropy in it. In fact, that's what it is. Anyway, let's look at these examples. In the first case, we have potassium bromate going to potassium and bromate. In this case, what we have is a solid forming aqueous ions. Aqueous ions are more random. They have more degrees of freedom than a solid. Here, they're confined in a crystal structure. Here, they're kind of floating around in solution. So here, entropy has increased. In case 2, we have 1 mole of gas forming 2 moles of gas. 1 mole of gas will have a certain amount of freedom, but 2 moles of gas will have more freedom. So therefore, we have increased the randomness, and we're looking for a decrease. In the next case, we have a liquid forming 1 mole of liquid forming 3 moles of gas. Liquid is more ordered than gases. Plus we have a lot more moles of gas. So in this case, we have increased the randomness. How about D? In D, we have 2 plus 1, and they're both gases, 3 moles of gas. So we have 3 moles of gas on the reactant side, and on the product side, we have 2 moles of gas. 2 moles of gas will be less random than 3 moles of gas. Another way of looking at this is we've kind of hooked these things together, right? So we started off with 3 things and we hooked them together to form 2 things. So these are less random. 2 moles of gas is less random than 3 moles of gas. So therefore, we've had a decrease in entropy. And E can't be true because we found that choice D was the correct answer. Question number 4 says, consider a reaction with a negative delta H and a positive delta S. Which of the following statements will be true? And the statements pertain to the spontaneity of the reaction at various temperatures. So let's take a look at what's going on here. Well, we need to know the equation. Delta G equals delta H minus T delta S. And we're told that delta H is negative value. And we're told that delta S is a positive value because this is negative delta H and positive delta S. And what we want to know is, when will delta G be negative? Specifically, at what temperatures will delta G be negative? So this is important. If delta G equals a negative, then we have a spontaneous reaction. So we want delta G to be negative. Well, what temperatures will that occur? Delta H being negative, that's helpful, right? That means that the reaction is exothermic, or it releases heat energy. Delta S being positive means that entropy increases, and that's good. So heat energy being released and entropy being positive means that delta G is going to be negative at any temperature. Mathematically, if this is negative and this is positive, so then this is negative here, so it's going to be a negative number minus a negative number, which means this is going to be always negative. So for this particular reaction, it will be negative, or spontaneous, delta G will be negative at all temperatures. However, I strongly recommend you think your way through this with a positive delta H and a positive delta S, a negative delta H and a negative delta S, and whatever other combination, I guess positive delta H and negative delta S, and think about at which temperatures will the delta G be negative. Sometimes, if delta H is positive, for example, and delta S is positive, high temperatures will tend to be favoring a spontaneous reaction. Why? Because T delta S term will become bigger than the delta H term if they're both positive. But in this case, with the negative and the positive, this is always a spontaneous process. I strongly recommend you think this through for the 4 cases, and it's certainly in your textbook where it's outlined for you. Question number 5 says, for the following example, identify the following. And it essentially wants the sign on delta H and the sign on delta S. So what we have is water liquid becoming water solid. So we essentially have water turning into ice from a practical perspective. So we're freezing water. That is what we're actually doing in this process. So let's think about the signs on delta H and delta S. So remember that delta H is enthalpy, the heat of the reaction. So if we look at this, if we have liquid water and we want to turn it into solid water, do we have to put energy in, making delta H positive, or do we have to take energy away, making delta H negative? That's how I think about it. In this process, we would want to take energy away from water. If you take energy away from water, or said another way, the liquid water releases heat energy, then it's going to freeze. If you put water in or heat into water, it's going to heat up, and eventually, if you put enough in, it'll turn into gas, steam. But in this case, we want to take energy away, or said another way, the liquid water needs to release heat energy. If it releases heat energy, the process is exothermic, and delta H is negative. Next, what about randomness? Liquids are more random than solids. So therefore, we have a decrease in the entropy. Since there's more degrees of freedom or randomness in a liquid, because the molecules have more ability to move around than they do in the solid, we have decreased the entropy of this system. So in both cases, delta H and delta S are negative. If you look at this in terms of the previous question, number 4, which I suggest you go back and watch before you listen to this section. So before we do that, I guess I should put that the answer here is A. Delta H equals minus T delta S. Well, if delta H is negative and delta S is negative, we want T to be relatively low. If T is relatively low, delta G will be negative, right? Because this is a negative and this is a negative. So T times negative, and this is negative, will give you a positive. If this value is too high, then delta G will not be spontaneous. So what do you do if you want water to freeze? You put it in the freezer where it's cold. Said another way, you put it at a low temperature. When you put it at a low temperature, it spontaneously freezes. But at a high temperature, in this case room temperature, it does not spontaneously freeze. So this is just another example of question 4, and in question 4 I talked about, think about all 4 examples. Well, this is the second example of question 4. Question 6 says, below what temperature does the following reaction become non-spontaneous? And we're given delta H and delta S. So we need to know that delta G equals delta H minus T delta S. And in this case, delta H and delta S are both positive. So as we talked about in questions 4 and 5, which if you haven't watched, you should consider to watch. When delta H is positive and delta S is positive, delta G can sometimes be negative. Said another way, the reaction can be spontaneous. But if this value is positive and this value is positive, but remember it's times negative T delta S, so this will overall be negative, this should be spontaneous at relatively high temperatures. Note that this is relative, right? Relatively high temperature could be room temperature, or it could be 10,000 Kelvin, but it's relative, so we can't say there's any value that's absolutely high temperature. But for relatively high temperatures for this particular process, this reaction will be spontaneous. Well, how do we figure out what that exact temperature is? Because it says below what temperature does this reaction become non-spontaneous? Well, we need to solve this reaction when delta G is 0. So before we do that, let's solve this reaction for T. All right. So the first thing I want to do is I want to subtract delta H. So negative T delta S, I'm simply just writing this on the other side, equals delta G minus delta H. Now I want to divide by negative delta S. So the negative cancels and the delta S cancels. So I want those to cancel. And what I get is T equals negative delta G minus delta H divided by delta S. So I put the negative out front because I moved the negative as well, and I put the delta S on the bottom. Okay, that's all well and good, but this isn't going to allow us to figure this out because we don't know the value of delta G, although I already said it. When delta G is 0, essentially the reaction is at equilibrium. But it's also going to be spontaneous at any temperature higher than that in this case because they're both positive. So we can find the tipping point, if you will. So we're going to set delta G to be 0. So what we're going to do is T equals negative 0 minus delta H, minus 136.5 kilojoules, divided by delta S, but it has to be in kilojoules. So you have to divide this by 1,000 because this is in kilojoules. This has to be in kilojoules per K. And if you do that, you get 0.2875 kilojoules per K. I simply divided it by 1,000. So I'm going to plug that in, 0.2875 kilojoules per K. Then, when you do this math, what you're going to get is T equals 475 K. So above 475 K, delta G is negative and spontaneous. Below 475 K, delta G is positive and non-spontaneous. This S is about non-spontaneous, but either way, it S is when the temperature, where the tipping point is, and in this case, it's 475 K. Question number 7 says, place the following in order of decreasing molar entropy at 298 K, and then we're just given a few gases. So, what do we need to know here? The higher the molar mass, the greater the entropy. So larger molecules have greater entropy than smaller molecules. And it's important because they're all at the same temperature that we can just compare them by molar mass. So this is decreasing. So decreasing means biggest first. So the one with the biggest molar mass is chlorine. Right, it's around 71. Then that's going to be greater than fluorine, which is around 38, which is going to be greater than hydrogen, which is around 2. So this is the order based on molar mass, and this gives us choice letter C as our answer. Question 8 says, calculate the standard entropy of the reaction below, and then it gives us the entropy for each of the species in the reaction. So this is your products minus reactants, like you did for delta H a long time ago. You can also do it for delta G, or you can do it for delta S. So here, delta S naught of the reaction equals the summation of N, the number of moles, times the standard entropy of the products, minus the summation of N, the number of moles, times the standard entropy of the reactants. So because entropy is a state function, essentially what we're saying is we're destroying the reactants, so they're negative, and then we're reforming those elements, so we're destroying them back to their elements, then we're reforming those elements to form the products. So here's what we need to do. We need to plug in these standard entropies multiplied by the number of moles. So the first thing is the product. C2H6 ethane. The entropy here, is 229.2 joules per K. Minus the reactants, the first reaction, C2H2, acetylene, is going to be 200.9 joules per K plus 2 times, why 2 times? 2 because there's 2 hydrogens, times 130.7 joules per K. When you do that math, you get that it's equal to negative 233.1 joules per K. So entropy has decreased because so this is negative. That makes perfect sense. We have 3 moles of gas, 1, 2, 3, forming 1 mole of gas. Entropy has gone down. So here we've gotten a negative entropy. And in this case, the answer to the question is A. Question 9 says, determine delta G naught reaction for the following reaction at 358 K. So this is similar to a previous question that we did, I believe number 6, except in that case we set it equal to 0, and here we're actually trying to find the delta G. So delta G naught of this reaction is equal to delta H naught minus T delta S naught. Well, before we plug in, we're given temperature in Kelvin, we're given delta H naught, and we're given delta S naught. We need to convert this to kilojoules. Why? Because this is in kilojoules, and our answers are in kilojoules. You could convert this to joules, but then you're going to have to convert your answer back to kilojoules. It's not wrong, and it's one small extra step, but I'm going to choose to convert this to kilojoules. To do that, I want to divide it by 1,000. So instead of this, I get 0.1602 kilojoules per K. Now I simply just plug into this equation. So delta H is 179.2 kilojoules minus T, 358 K, times 0.1602 kilojoules per K, the delta S. And when I do this, I find that the delta G of the reaction is equal to 121.8 kilojoules. Note that this is a positive value, so this isn't a spontaneous reaction. In this case, both delta H and delta S are positive, so this would only be spontaneous at high temperatures. It turns out that 358 K is not a high enough temperature to make this spontaneous because delta G is still positive, so the answer here is choice letter E. Question 10 says, in the Haber process, ammonia is synthesized from nitrogen and hydrogen. And this is the reaction. It says delta G naught at 298 K for this reaction is minus 33.3 kilojoules per mole K. The value of delta G at 298 K for a reaction mixture that consists of 1.9 atmospheres of nitrogen, 1.6 atmospheres of hydrogen, and 0.65 atmospheres of ammonia is. So the standard enthalpy of formation is useful because, this standard Gibbs free energy is useful, but it only works when things are at 1 atmosphere and we're at 298 K and all this kind of stuff. So it's not always the case. One really classic example of this is water. We know that water spontaneously evaporates, right? If you spread some water out, if you spill some water and you wipe it on your countertop, it spontaneously evaporates. We know that. But if you look at the delta G naught, it's a positive value. Well, why is that? Because the pressure of water in the atmosphere is not 1 atmosphere, because delta G naught assumes 1 atmosphere of pressure. Since water vapor doesn't have a pressure of 1 atmosphere, it can spontaneously evaporate. Said another way, delta G naught and delta G are not always the same. Well, how do we relate those things? Well, there's an equation for that. Delta G equals delta G naught plus RT ln Q. And Q is very similar to K, except it's right now instead of at equilibrium. So in our case, Q, its products over reactants, is the pressure of NH3 divided by the pressure of N2 times the pressure of H2 cubed. So it's the same as K for an equilibrium process. These are all gases, so they're all in it. The only difference is it's not at equilibrium. It's at whatever time, in our case, this time with these specific pressures. A couple other things to remember. R that you want to use here is 8.314 joules per mole K. However, because our units are going to be in kilojoules, okay, so the delta G naught is in kilojoules, the R we're going to want to use is divide this by 1,000, which is 0.008314 kilojoules per mole K. Now, if you'd like to convert this to joules, that works too. It's totally fine, but at the end you are going to have to convert your answers because the answers are all in kilojoules, even though I'm just noticing now that's not clear, but because they're not labeled. They probably should be. Anyway, let's go ahead and do this. So the first thing we need to do is we need to find Q. So to find Q, we need to plug in what we know. The pressure of ammonia, which should be squared because there's two of them, is going to be 0.65 squared over the pressure of nitrogen, which is 1.9, and the pressure of hydrogen times 1.6 cubed. And when you do that math, you find that Q is 0.054. So we can now plug in. Delta G equals delta G naught, which is given, right, minus 33.3 kilojoules, plus R, I want to use this one, 0.008314 kilojoules per K, times 298 K, the temperature of this reaction, times the ln, that wasn't very good, the ln of Q that we just found, which is 0.054. What we find is delta G equals minus 33.3 kilojoules plus negative 7.23 kilojoules, which is what you get when you multiply this times the ln of this. Then we get delta G equals negative 40.5 kilojoules, which is choice letter E. And if you had this as per mole here and per mole here, that's totally fine if you wanted to do it kilojoules per mole instead of just kilojoules. So this is how we would solve question number 10. Question number 11 is essentially a definition. Give the name of a reaction that achieves the theoretical limits with respect to free energy in thermodynamics. This is a reversible reaction. And it's important to point out that many reactions are irreversible because of heat loss. Okay, so they're not achieving the theoretical limits with respect to free energy in that case. But a reversible reaction is achieving those theoretical limits. Question number 12 says, calculate the standard Gibbs free energy of the reaction using the following information. And this is very similar to a previous question we did, specifically question number 8, where we did this for entropy, but here we're going to do it for delta G. So delta G naught reaction equals the summation of N, the number of moles, times the standard Gibbs free energy of formation of the products minus the reactants. So these are the values. Now notice that we're given the Gibbs free energy of formation of both reactants and one of the two products. Why aren't we given the other one? Well, the other one is an element. So for elements, just like for delta H, the delta G is 0. So the delta G naught of the reaction equals 7 times 0, so we don't need to put that in for the first product. And then for the second product, we need to do 12 times minus 237.1 minus, now for the reactants, 4 times minus, this should be kilojoules, and it should be 4 times minus 73.5 kilojoules plus 5 times 149.3 kilojoules. And when you do all that, you find that the delta G naught of the reaction is equal to negative 3298 kilojoules. But because the answers are in scientific notation, we have to move the decimal place 3 times. So it's negative 3.298 times 10 to the 3 kilojoules, which is choice letter B. All right, so now we're going to switch gears into electrochemistry. And we're also going to do question number 14, which is really long. All right, it says, determine the oxidation state of carbon in carbonate, CO32 minus. So the oxidation state of carbon plus 3 times the oxidation state of oxygen, because there's 3 oxygens, equals the charge, in this case negative 2. So generally speaking, the oxidation states of the elements equals the overall charge on the species. It's really important to remember that oxygen virtually always has an oxidation state of negative 2. There are some exceptions to that. I wouldn't put those exceptions in, so I would just assume oxidation state of oxygen is always minus 2. So the oxidation state of carbon plus 3 times negative 2, the oxidation state of oxygen, equals negative 2. Carbon's oxidation state minus 6 equals negative 2. Add 6, add 6. Carbon's oxidation state equals plus 4. So this is how you can solve for the oxidation state of carbon in carbonate. Note that the oxidation state of carbon is not always plus 4. Try carbon monoxide, for example, CO, and you'll find that it's not exactly plus 4. Question number 14 is a redox balancing question, and you can might see I zoom the camera out because we're going to need the whole rest of the paper to do this one. This is a really long problem, but I do want to go through an example so you have it, and I picked a harder one. I picked basic solution instead of acidic solution because that adds a step. So it says balance the following redox reaction if it occurs in basic solution. What are the coefficients in front of CrOH4 minus and ClO minus in the balanced reaction? So the first thing that we want to do is we want to figure out what's being oxidized and what's being reduced. And I strongly recommend, if you haven't already, you watch question number 13 to figure out how to find the oxidation states of things. Okay, and if we look here, what we'll find is the oxidation state of chromium on this side is plus 3, and the oxidation state of chromium on this side is plus 6. Okay, so in this case, we have lost electrons and oxidation is losing. So you may have heard Leo the lion says grr, losing electrons is oxidation. So this is our oxidation half reaction. Then we have to look at Cl for our reduction half reaction. In the case of ClO minus, it's plus 1, and in the case of Cl minus over here, it's minus 1. So here we've gained electrons, 2 electrons to be specific, and this is reduction. Again, if you're not sure how I got these numbers, please revisit question number 13 where we talk about that. In this case, hydroxide is -1, OH minus is -1, or you can think of oxygen as -2 and hydrogen is +1, but that's a little bit harder. Here, oxygen is -2, here oxygen is -2, here it's by itself, so it's easy to find the oxidation state. All right, so that gives us what's oxidized and what's reduced. Now, we need to break this up into the 2 half reactions. So for the oxidation half reaction, essentially what we have is we have CrOH4 minus forming CrO4 2 minus. So this is going to be our oxidation half reaction. In the case of our reduction half reaction, it's the other one, we have ClO minus, aqueous, forming Cl minus, aqueous. So that's our reduction half reaction. Now we need to balance the elements in both of these half reactions. So in this case, what we need to do is we need to balance essentially the oxygens, hydrogens, and chromiums, but the chromium's already balanced. So let's look at the oxidation half reaction. We're going to try to balance the elements. We have Cr, OH, 4 minus aqueous, forming CrO4, 2 minus aqueous. What's the difference? Well, the difference is 4 hydrogens. So when there's 4 hydrogens, we need to add, we can add acids, bases, and water. Acids first, and then we can make it basic. So in this case, what do we want to do? Well, we want to balance this by adding 4 H pluses. So we have first want to assume that we have an acidic solution, and because this has 4 hydrogens and this side has no hydrogens, they both have 4 oxygens, they both have 1 chromium, those are already balanced, so now we need to add 4 H pluses to balance the hydrogen. But then what we want to do is we want to make it basic. And how do we make it basic? Well, we add OH minus, 4 OH minus to both sides. So in this case, we get 4 OH minus aqueous plus CrOH 4 aqueous, that's minus, yields CrO4 2 minus aqueous plus the 4 OH minus that we had to this side react with the H plus, and we get 4 H2O liquid. Okay, so that's how we take care of that. Now for the reduction reaction. For the reduction reaction, we have, I'm going to put it a little further over so I don't run out of space like I almost did here. We have ClO minus aqueous, and we have it forming Cl minus aqueous. So how do we fix this? Well, if we notice here, we have a O here and no O here. So what do we add there as O in it? Well, we add H2O liquid. We then need to balance the H. Since we added 2 H's, we have to add 2 H plus aqueous on this side. Now we need to make it basic. So we add 2 OH minus to this side, and we get 2 H2O liquid, because the OH minus and the H plus give us water, plus ClO minus aqueous yields Cl minus aqueous plus H2O liquid plus 2 OH minus aqueous. So we added 2 OH minus to both sides. The OH minus on the reactant side turned into water. The OH minus is over here. Finally, we can we could simplify this by crossing out the waters, but that's not entirely necessary at this point because we can cross out the waters a little bit later on. So we have 2 waters here and 1 water here. All right, so the next thing we need to do is we need to figure out how many electrons we need. So we're going to start that, and I'm going to use a lot of this space with the oxidation reaction. So I've done the oxidation and the reduction, Now I'm going to go back to the oxidation after it's basic. So what I have is I have 4 OH minus aqueous plus CrOH 4 minus aqueous yields CrO4 2 minus aqueous plus 4 H2O liquid. Now count the charges. Over here I have 4 minus plus another minus, which is 5 minus. Over here I have 2 minus. They don't match. The whole idea of balancing redox equations is to make sure that these things match. So I need to add 3 electrons, because that'll give me 3 more minus. Now I have 3 minus, 5 minus, 4 minus, 5 minus. They match. So we're in good shape. Now for the reduction half, I have 2H2O liquid plus ClO minus aqueous yields Cl minus aqueous plus H2O liquid plus 2OH minus aqueous. Count the charges. It's 1 minus on this side and 1, 2, 3 minus on this side. So I have to add 2 electrons. It's very important that on the oxidation half we add the electrons as a product, and on the reduction half we add the electrons as a reactant. If that's not true, then we've misidentified the oxidation and the reduction reactions. Now I need to make these balance so that the electrons will cancel out. So I need to, for the oxidation half, to get a common denominator of 6 between 2 and 3, I need to double everything. So I need 2 times the oxidation. So that'll go through 8 OH minus aqueous plus 2 Cr OH4 minus aqueous yields 2 Cr O4 2 minus aqueous plus, I'm doubling everything, 8 H2O liquid plus 6 electrons. Now for the reduction half, I need 3 times the reduction because it's got 2 and I want it to be 6, so it'll cancel out when I add the reactions back together. So I want it 6 electrons, multiplying everything by 3, plus 6 H2O liquid plus 3 ClO minus aqueous yields 3 Cl minus aqueous plus 3 H2O liquid plus 6 OH minus aqueous. So I literally just multiplied everything in this one by 3 and everything in this one by 2, and this is what I got. Now I can add the 2 reactions together. Note that when you add reactions together, you simply write everything on the reactant side and everything on the product side on their product side. So I'm going to start with this. 8 OH minus aqueous plus 2 Cr OH4 minus aqueous plus, now I'm going to squeeze up to the other reactants, 6E minus plus 6 H2O liquid plus 3 ClO minus aqueous. So I've written everything on the reactant side on the reactant side. I'm going to need 2 lines here, but now I'm going to write everything on the product side on the product side. Yields. I'm going to start up here. 2 CrO4 2 minus aqueous. I'm going to go over here with this one, plus 8 H2O liquid plus 6 E minus plus, now the other ones, 3 Cl minus aqueous plus 3 H2O liquid plus 6 OH minus aqueous. Now I want to cancel out like terms. Well, if I look here on the reacted side, I have 8 OH minus, and over here I have 6 OH minus. So I'm going to cancel out all 6 of these and change that to a 2, because the other 6 aren't really reactant, right? They're just going from one side to the other. I'm not going to find any more CrOH4 minuses, so that one doesn't do anything. The 6 electrons cancel out. That's the whole point here, is to cancel out the electrons, because you can't actually have electrons in the balanced chemical equation during the redox balancing. How about the waters? Well, I have 6 waters on this side, and I have a total of 8 plus 3 electrons, waters over here, which gives me a total of 11. So I'm going to cancel out all 6 waters on this side. I'm going to cancel out these 3 plus 3 more, which gives me 5 waters on this side. ClO minus, you're not going to find it again. CrO4 2 minus, you're not going to find it again, and Cl minus, you're not going to find it again. The only things you're going to find are OH minus in the case of a base, water, and electrons. So now I rewrite, simplifying. 2 OH minus aqueous plus 2 Cr OH 4 minus aqueous plus 3 ClO minus aqueous yields 2 CrO4 2 minus aqueous plus 5 H2O liquid plus, and I'm going to have to write it down here, 3 Cl minus aqueous. All right, at this point we can check our answers. A couple things you want to check. 1, you want to check the charges, and 2, you want to check the atoms are balanced. So let's take a look. We have 2 minus, and 2 minus is 4 minus, plus 3 minus is 7 minus. In this case, we have 2 times 2 minus, which is 4 minus, plus 3 times 1 minus, which is 3, so 7 minus. So they balance out. We have 2 chromiums here, 2 chromiums here. We have 3 chlorines here, and 3 chlorines here. How about oxygens? We have 2 oxygens, plus 2 times 4, which is 8 oxygens, so 10 oxygens, plus 3 oxygens, which is 13 oxygens. Over here, we have 2 times 4, which is 8, plus 5 more, which is 13 oxygens. We have successfully balanced this equation in just a tiny amount of work. Okay, these are really a pain in the neck. Adding the step of making it a base does add 1 step. You wouldn't have to make it basic if it was an acidic solution. But to answer the question, what are the coefficients? Well, if we look at CrO4 minus, it's got a 2 in front of it. And if we look at ClO minus, it's got a 3 in front of it. So 2 and 3 are the answer, which is choice letter B after all of that work. I'm going to zoom the camera back in and come back with number 15, which is more just a definition. Number 15, a much easier question than number 14. It's just a definition. It says identify the location of reduction in an electrochemical cell. The area of reduction is called the cathode. The area of oxidation is called the anode. That's something you just kind of have to remember. Number 16 says, use the standard half-cell potentials listed below to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees C. So the equation is E naught cell equals the standard reduction potential minus standard potential of the oxidation. So we need to find out where oxidation and where reduction are occurring. In order to do that, we need to know oxidation states. And if you go back to question number 13, I talk about how to actually find the oxidation states. Here I'm just going to kind of give them. So what we need to know is that elements have an oxidation state of 0. So the oxidation state of chlorine and the oxidation state of iron are 0 because they're both elements. And I guess in this case you don't actually need to calculate anything. Here, chlorine is -1 and iron is +3. They're given. So in this case, iron has gone from 0 to +3. This means it's lost electrons, and oxidation is losing, or losing electrons is called oxidation. Leo, the lion, says Ger, gaining electrons is reduction. So this is oxidation, and this is occurring at the anode. In this case, chlorine has gained an electron, so this is reduction, and this is occurring at the cathode, which is from question 15. So now we can just plug this in. The reduction potential here is 1.36 volts for what's being reduced, and for oxidation we have -0.04 volts, and when we do this math, simply just add them, I guess, together, we get the E naught of the cell is equal to 1.40 volts. So here the key is to figure out where oxidation and reduction is occurring. In this case, it's fairly straightforward because we're given the oxidation states of the ions on the product side. Sometimes we'll be given the counter ions as well, so we may not know the actual oxidation states. We'll have to figure them out as we did in a previous question, specifically question number 13. Question number 17 says, determine which of the following pairs of reactants will result in a spontaneous reaction at 25 degrees C. So I'm not sure if you're given this, or I can't imagine you have to memorize it, but you're going to need a standard reduction potential table in order to do this question. So I'm going to go over that, but I'm not sure how that's going to apply to your actual exam. So let's take a look at this. We have zinc, which is here, and potassium, which is here. And what you want to pay attention to is which one has the charge. So potassium is positively charged, so will it take an electron away from zinc? In order for potassium to take an electron away from zinc, it would need to be higher on the standard reduction potential because there's stronger oxidizing agents in this direction, meaning that their ions can take electrons away from things because an oxidizing agent is itself reduced. So if we look here, we have zinc here and we have potassium down here. Potassium ions, sorry, you're not seeing it, potassium ions are way down here and zinc is here. So potassium ions have a lower reduction potential and therefore are not going to be able to take electrons away from zinc. Just to put this into perspective, if you look way up here, things like gold, which are very hard to oxidize, which is why gold is valuable, are way high on the periodic, or way up here on this table, which means it's really hard to take electrons away from them, which is why they don't oxidize, which is why they're used in jewelry and also for electronic circuits and things like this. Okay, so potassium's not taking an electron away from zinc because potassium's lower on the table. Let's look. Copper 2+ and zinc. Copper 2+ is higher than zinc on the table. So copper 2+, sorry, I realize I don't have this whole thing on the screen. Copper 2+ is higher than zinc on the table. So copper 2+ is going to take electrons away from zinc because it has a higher reduction potential. It's a stronger oxidizing agent. Therefore, it's more likely to be reduced. It'll take electrons away from that zinc. So this is our answer. Chromium and lead. If we look at our table here, chromium 3+ is here and lead is here. So chromium 3+ is lower on the table. It's not going to be able to take electrons away from lead. And then finally, iron and barium 2+. Iron is here, and barium is way down here. So barium is not going to be able to take electrons. Sorry, barium is way down here. This is bad, not having the whole sheet on the table. The whole sheet on the screen. So the barium is lower, the iron is higher, so the iron can't take electrons away. So copper can take electrons away from zinc because copper is higher on the table and zinc is lower on the table. So that is our answer. Number 18 says, which of the following metals will dissolve in nitric acid but not hydrochloric acid? And we have aluminum, magnesium, silver, iron, and zinc. So here's what you want to do. What we're looking for is comparing the reduction potential of hydrogen versus the reduction potential of nitrate. So nitrate is an oxidizing acid. Nitric acid is an oxidizing acid because the nitrate can also oxidize things, not just the hydrogen. So any metal that's lower on the list than hydrogen will be oxidized by hydrogen, very similar to what we talked about in question 17. So if we look at the examples here, we have aluminum. Aluminum is lower. It'll be oxidized by hydrochloric acid. Magnesium, you've actually done this, and if you took the Gen Chem lab here, magnesium is lower. It will be oxidized by hydrochloric acid. I'm going to skip silver. Iron. Iron is lower, so it will be oxidized by hydrochloric acid. And zinc. Sorry, I realize I'm not on the screen. This is driving me crazy. So iron is lower, zinc is lower, magnesium is lower, and aluminum is also lower. So all of these are lower than H+, so they'll be oxidized by hydrochloric acid. But what about silver? Silver is higher than hydrochloric acid, and silver is a more noble metal, things used in jewelry. All right, so because it doesn't oxidize easily, so hydrochloric acid will not oxidize it. But nitric acid will oxidize the silver, and the reason for that is the nitrate itself is a strong oxidant. So that's why nitric acid is considered an oxidizing acid, and it's very commonly used. It can be used to oxidize metals. So in this case, the answer here is silver, and I apologize because I have the screen too zoomed in so you can see, and I'm missing the table. All right, question 19 says, identify the characteristics of a non-spontaneous reaction. Identify the characteristics of a spontaneous reaction. This question is a memorization one again. All right, so we have E cell is greater than 0. When it's greater than 0 or positive, the reaction is spontaneous. K, the equilibrium constant, is greater than 1. If it's greater than 1, it's going to be spontaneous in the forward direction or spontaneous. Delta G is less than 0. When delta G is negative, reactions are spontaneous. So all three of these things mean that the reaction is spontaneous, and this hopefully shows you some of the interrelationships between delta E, K, and delta G. So question 20 is similar to 19. It says, which of the following reactions would not be spontaneous at 298 K? Well, if E cell is greater than 0 or positive, then it is spontaneous. If E cell is less than 0 or negative, then it's non-spontaneous. So in this case, it's the only one with a negative E cell is choice letter A, so therefore this is the non-spontaneous reaction. Question 21 says, how many electrons are transferred in the following reaction? The reaction is unbalanced. So this is very similar to a balancing redox question that we did a few questions ago, that really long one. But let's take a look. First of all, we need to find out what's oxidized and what's reduced. So calcium has an oxidation state of 0, and it goes to +2. So in the case of calcium, it has lost electrons, so it's been oxidized, which means that it is the anode. Chromium has gone from +3 to 0, which means it's gained electrons, or it's been reduced, which means it's the cathode. Not that you need to know if it's the anode or cathode, but it's just a good reminder in my opinion. All right, so the oxidation half reaction is calcium forming calcium 2+. And the reduction half reaction is chromium 3+ forming chromium. And normally we do a second step where we balance the elements, but the elements are balanced, so we're good. Then we would do another step where we would balance the charges. Well, in this case, the calcium forms calcium 2+ plus 2 electrons. And to get calcium 3+ to form chromium, we have to add, chromium 3+ to form chromium, we have to add 3 electrons because we have to make the charges equal. So here it's 0, so +2 minus 2 is 0. Here it's 0, so +3 minus 3, it's 0, if you want to think about it that way. Well, what's the lowest common denominator between 2 and 3? If we were to further balance this, we would multiply this by 3 and multiply this by 2, which means that a total of 6 electrons have been transferred, because we would multiply this by 3 and we get 3 Ca solid plus 3 yields, 3 Ca2+ aqueous plus 6 electrons, and here we would get 6 electrons plus 2 Cr3+ aqueous yields 2 Cr solid. So in this case, we have to transfer 6 electrons. We could then just add these together, and the only thing that would cancel out is the electrons, because we didn't have to balance the atoms because there's no oxygens here. So the answer here is 6. If you want to go through the entire redox balancing, you can do that, we essentially just did that. I just did it in a more abbreviated way in the interest of time, because if you remember back to the previous question, it was like 15 minutes long. It says the standard EMF for the cell using the overall cell reaction below is plus 2.2 volts. The EMF generated by the cell when the concentration of Al3 plus is this and the concentration of I minus is this is how many volts. So we're essentially asked to compare the E cell of the current conditions, these concentrations, with the E cell of the standard cell, which is given 2.20. In order to do that, we have E cell equals E naught cell minus 0.0592 volts over N, the number of moles of electrons transferred, log Q, where Q is just like K, except it's current conditions and not equilibrium conditions. So it's products over reactants. So in our case, Q is the first product, which is the concentration of Al3 plus squared, times the second product, the concentration of I minus, to the sixth, over the reactants. But if you look here, both of these reactants are not aqueous or gases, so they don't go in our equation. So it's basically over 1. Now we can plug in. Q equals the concentration of Al3 plus, which is 4.5 times 10 to the minus 3, and that's going to be squared, times 0.15 to the 6th power. And if you use your calculator to do this, you find that Q equals 2.3 times 10 to the minus 10. So that gives us this value. We have this value. This is a constant. So we need N. How many moles of electrons were transferred? Well, here we had 2 of these going from 0 to 3 plus, but there's 2 of them. So essentially they've lost 6 moles of electrons. Here we have 3 of these at 0 going to 6 of these at minus. So each I has gained an electron, so we've transferred 6 moles of electrons. We now have everything we need to know to solve this problem. E cell equals the standard potential, 2.20 volts, minus 0.0592 volts over N, which is 6, times the log of Q that we just found, which is 2.3 times 10 to the minus 10. When we do all that math, we get E cell equals 2.20 volts minus 0.094 volts, and E is equal to, excuse me, this should be plus, is equal to 2.29 volts. Notice that these conditions don't change the E very much, and that's pretty common. So they can change it, but they don't change it a whole lot. So I hope you found this useful. I know we didn't go over everything in a lot of detail, but the video is still an hour long. I did want to go through everything in a kind of concise way, so it's a broad overview. These questions can be challenging because they're very similar with similar equations, balancing redox equations, delta G naught versus delta G, and some certain conditions, and all this kind of stuff can be challenging. The best thing to do when you have a lot of similar stuff all at the same time, unfortunately, it's not the easiest thing to do, but it's the best thing to do, and that is practice. So I strongly recommend you practice some of these problems. You can find them in your textbook, Alex, wherever, but practice some of these problems, because if you do these a few times, they're not so bad. If you do them once or twice and then you go into the exam, this can be very challenging. So I want everybody to be successful. So I strongly recommend practice, practice, practice. Thanks for watching. I hope you enjoyed general chemistry. And again, I hope to see some of you in organic chemistry, specifically in my case, the lab, in the future. Thanks.